Cool. So we are given a list schedule of employees, okay, which represents the working time for each employee. Okay, so it's like schedule 0 element will kind of contain the working time of 0th employee. Each employee has a list of non-overlapping intervals. Each employee has a list of non-overlapping intervals, fair. And these intervals are in sorted order. Okay, return the list of finite intervals representing common positive length free time for all employees. So let's first understand our output here, because when these questions get too real, it kind of becomes slightly difficult to understand them. So what you have to return is a list of positive length free time for all employees. So it's like I1 or say or I1 E1 or say S1 E1, right? This is start and end, and say S2 E2 and say SN EN. This is what they want as return, where now S1 and E1 should, or SI and EI should not essentially should not exist, or should not be overlapping with any working time of any employee. Right. Okay. So one thing that I can think of is, as we go through employees one by one, given their times are sorted, we can generate candidates from first employee itself, and then we can keep shortening the intervals of candidates or add new candidates. By the time we have processed all, we'll have a list of candidate intervals that don't lie in any of the employees' work schedule. Even though we are representing intervals in the form of xy, the objects inside are intervals, not lists or arrays. For example, schedule 0 in 0th employees 0 dot start is equal to 1, schedule 0 0 end equals to 2. Oh yeah, schedule of 0th employees, his 0th interval of working, start is 1 and end is 2. Object inside are intervals. Oh, okay. They are these classes basically. They are not like, that's what they meant. Okay, it's not a list. Also, we wouldn't include intervals like 5 5 in our answer because they have 0 length. Okay, that makes sense. So remove any candidates having 0 length. So now if this is given to us, schedule and say first employee, and let's just keep like this. So first employee's work timings are 1 2 and 5 6, and the second employee's work timings are 1 3 and 4 10. Right, so what I was proposing here was that we can go through this list, right, and given that our our starting for any schedule starts with 0, it can be 0 and ending can be 10 to the power 8. uh, 410. That's how it is, yeah. There are a total of 3 employees, and all common free time intervals would be minus infinity to 1, 3 to 4, and 10 to infinity. We discard any intervals that contains infinity as they aren't finite. Okay, okay. So actually, once we come here, right, come and realize the first thing here, then we can make an interval there, which is minus infinity to 0. Right, at 1 they start working, so 1 can't be a interval. But here 3 to 4 is considered an interval, so I think when 3 to 4 we are considering, it's not existing here, but 4 exists here, so they can be starting points. So infinity to 1 is 1. Then when we proceed to the next interval, we check the starting time of this minus ending time of previous, so that gives us the thing. So like starting would obviously be after this, which is 3, and ending would be before this, or at that, actually say 2 to 5. That's his break times. Now the next thing we'll have is we'll go to the next employee, which will give us minus infinity to 1. So this becomes common, and then he'll give 3 to infinity. And this guy will give minus infinity to 4 and 10 to infinity. Now how do we come up with 3 to 4? This is a good question. Essentially, if you were seeing this on a number line, then say this was like 1, 2, 3, 4, 5, 10. Say 10 is here. Then we have one free which goes like this, another one which goes till 2 to 5, another one which goes to 3 to infinity, and the one which goes from minus infinity to 4, and 10 to infinity. Now we can clearly see that 3 to 4 is like one period. So this was by first guy, this was also by first guy, this was by second guy, or this is also by second guy actually. First and second, okay. This is by third, this is by third. If you see, the only place where first, second and third all three are intersecting is this 3 to 4 period. It's easy to visualize this, but how do we solve this? So given I've kind of gone through first and made these candidates, I need to only add those candidates which intersect with these, because otherwise anyway first won't intersect. Like if say something like this comes up, first is not going to intersect with it, it makes no sense. So for every new interval and every new candidate interval that we get, so from second if we get minus infinity to 1, That is an intersecting interval, so we'll keep that. uh, but from second, when we get this like 3 to infinity, we're gonna check whether 3 to infinity has an intersection with any of the intervals previously, which now it has to change 2 to 5 toward, somehow it has to change 2 to 5 toward 3 to 5. How will we do this? And these intervals can be very long, like they can go till 10 to the power 8. I'm feeling we need to do something of like, hmm, if for every candidate interval we have to go through every previous interval to see if there's some intersection, that will make it n square. Not really n square in a way, because for every interval we'll just be checking the candidates. And what if candidates are like n, like all of them have the same free slot, then you are checking n time, like then it's getting n square. Yeah. So in the worst case, in that case, we'll have n square, which does not seem like a very good idea. It'll mostly go time limit exceeded, because if this is going till 10 is power 8, there's a good chance it won't accept it. So what are we doing there, which is a like duplication of efforts? Let's just try to think from that aspect. As because we have to get this down to O of n, or max to max O of n log n in some sense. So when a new interval comes up, right, you need to make sure you need to just check directly if that exists first of all. Otherwise, you need to kind of see where that will lie. Now, once you have a starting and the ending point, like if I have a 3, right, I know that I in the previous candidate slot, as long as candidates are sorted, I can find a 3, or if I can't find a 3, I can find a uh, maybe I can find closer to 3. I can do a binary search there and find something that starts around at 3 in log n time. Right, once I find that, I can check when it ends. So instead of doing n, I'm doing n log n now. Right, so n log n might suffice. Once I do a log n, I find the interval, I can check, like say, uh, initially I'll have this as my candidate. So let's say candidates will be something like this. And now a new interval will come up as we'll be processing the second guy, which is 1 3. We'll get the first interval, which is minus infinity to 1. Since it has infinity, we're gonna yeah. So since we have here, and what's happening, let's get back to this. Yeah, so minus infinity to 1 and 2 is power 5. Actually, uh, what if somebody else comes up with the 0 to 1 that intersects? So we need to keep this. We'll disregard all the infinity ones later on. So now when new thing comes up and we get a minus infinity to 1. Say we are able to form that, right, based on this guy. Uh, then essentially we need to do a binary search for minus infinity, or we need to do a binary search for the end point. That's what I'm thinking about. Will we do a binary search for the starting point or on the end point? We can do for either. Let's just do a starting point, for example. If we do, and it's gonna find this guy. When it finds this guy, we're gonna see what's the intersection between these and these. So binary search login, then it tries to find intersection, which is going to be like for intervals s1 e1 and s2 e2. This is gonna be max of s1 s2 and min of e1 e2. Right, correct. So max of s1 s2 will be minus infinity. Here min of e1 e2 will also give us 1 only. We'll get that correctly. Now the next one comes up, which comes up as 3 to infinity. So when 3 to infinity comes up, we'll again check on the starting point. We'll try to search for 3. We won't find 3, but then we'll be able to find either like we'll find this index probably as the next best thing. So once we find this thing, what we're going to do is we're going to do a intersection here. So 2 to 5 and 3 to infinity. So that will give us a max of s1 and s2, which is 3, and min of infinity and 5, which is 5. So that way we'll have this intersection, and that becomes a new interval, right? And so that's how we are actually changing the candidates interval that we find using binary search. So find intersection and change this index found via binary search. And finally, when we are done processing all employees, we can parse through the candidates and create a new list, ignoring the single length, ignoring ones having 0 length or infinities or minus infinity. Okay, time to probably code this. Why does it? Oh, it's a list of interval. Okay. Okay, so candidates for employee sched in schedule is essentially, yeah, the first guy, right? What we're gonna do is for work interval in employee schedule, what we can do in this case is, like, the first one is coming up, we need to just get start end of work interval. So here we can probably use an I, because the first one will have infinity and the other one won't. So if I is equal to 0, we'll have a special case. If I elif length of employee schedule minus 1, we'll have a special case here, special case here. Else we're gonna base it on previous guy. So when we are processing 5 or 6, what we have to do is the free time will become free time candidate is basically like employee sched I minus 1 will itself be an interval. Now this interval dot end comma current one, so work interval dot start. This becomes our free time candidate. If it's the last thing, then free time candidate is work interval dot end comma float of infinity. And if it's the starting case, then free time interval is float of minus infinity and the work interval dot start. Right. So once we have a candidate for a given once we have one candidate, what we can do is we have to try to search it, right? So if not candidates, if there's nothing in candidates right now, we're gonna just add it. So candidates dot or in this case also, like as long as we are just processing the first guy, we have to just add the candidates. Second guy onwards things change. So for index enumerate if index is equal to 0, basically the first employee, then we just add it. Right. Else binary search logic, which we'll just finish right now. So say we are able to binary search and change the intervals, then this is all we are doing, right? After this we have to pass through the candidates for interval. They want us to give an interval only, so let's create an interval here. Or we can do that later. So for interval and candidates output list, if interval 0 is float of minus infinity or interval 1 is float of infinity or interval 1 minus interval 0 is equal to 0, then you have to just continue. Else what we're going to do is we have to convert this into an interval, proper interval, and append it. So output list dot append interval, which is going to have a interval 0 as the starting and interval 1 as the ending, and we can return this output list. Now the thing that's pending is this binary search logic, so we should probably use bisect here because otherwise it's too much. Import bisect. So bisects, let us do binary search. Now what we want to do here is, once we find a free time candidate, right? And this is not, index is not 0. So what we are going to do here is try to find its starting point. So bisect dot bisect left, and this is where I have gotten stuck because I don't remember the definition of bisect. So maybe right now we are just practicing, so it's okay. We can just check through this and learn what happens. Uh, locate so for bisect left, it's like locate the insertion point for x in A to maintain sorted order. Parameters low and high specify a subset of the list which should be considered. By default entire list is used. Okay, bisect right is similar to bisect left. Bisect is equal to bisect left, but returns an insertion point which comes after to the, actually bisect right and bisect are the same. So these two are the same, and they first take, so x is the key you want to find and a is the thing, a is your array, and this returns an insertion point which comes to the right of any existing entries of x. Do you want to do afterwards or do you want to do before? And this will do to maintain sorted order. So if you use bisect, the thing is it can give us something like, the bigger problem I have here is, what if you want to have bisect but it's not a simple array here? How do we do that? Uh, okay, sadly bisect will only work with, so okay, now candidates have, yeah, actually we are fine. Candidates in our case will only have list of regular intervals. It's not like these intervals, these kind of interval classes. So then we can kind of work with it. It would have been good actually if we would have used tuples here, because no. Yes, no, oh yes. Come on, come on. I am not sure if we can use bisect on intervals. Uh, it sucks if we have to write the binary search ourselves. Sucks. What if when I maintain candidates, I also maintain candidates starts? Right, so wherever candidates is getting appended, I'm gonna append. free time interval 0. So now I can do. So this is like O of an extra space, but it's fine. We were anyway using this. So A and our X is going to be free time candidate 0, right? This is gonna give us a value after which we have to check. Now this will give us index, some index, right? And if we inserted that index, everything after that will anyway shift. So we have to kind of check with the same index. So we want to check for the same index. So in that case, maybe we just add some print debugging. Yeah. Right. So once you find the index, right? So index, what do we do with the index once we find a free time candidate? Uh, come on, come on, come on, come on, come on. What do we do with this? Let's just look at my notes. So when we search find intersection, yeah, you have to store the intersection. So we're gonna change candidates index to max of whatever existed 0 and the current interval. So free time candidate 0 and min of one and free time candidate 1. And now that we have changed this, we need to change candidate stats index also. 0. Right, so this will change all the indexes. Should probably debug these, so let's add candidate starts looks like this, value finding is this, index returned is this. So we'll know if we have to do it for index or index plus 1. That is the only worry I have. And let's just try to run this and see what we have, what we get. Fine, that's not a problem if you're getting, we'll fix things. So 1 2 can actually let's just print maybe for print candidates right. So initially there's no candidates, then after 1 we have a minus infinity to 1 and 6 to infinity. Then for the second guy it comes up here. Now candidate, what's happening here? Let's do this after this guy and minus infinity minus, why didn't it give 2 to 5? What the hell? So if I is equal to 0, when I is equal to 0, it's going to be 1 to 2. Oh, okay. Okay. Understood. So these are some extra conditions, but we always have to. This is like an extra thing if it's not 0. But if it's anything other than 0, we will have a previous employee. So some issue happened. So minus infinity and 6 still not happening. Oh, we are replacing this. That's the problem. Okay. We always have an extra pre-time candidate in case of I equals to 0. This is a nice problem. So it's not always going to be free candidates, but it's going to be free candidate list, sadly, as much as I would have liked it to be 1. So what I've done is we'll try to process both. So sometimes this extra one can come up in the end. And so I've kept it as free candidate now instead of free time candidate. And let's just see what happens now. Right. Candidate charge would append second free time candidate. Where is this happening? 931. Here. So if this is this we can push here. Right. Minus infinity to 1, 2 to 5, 6 to infinity. Candidate starts minus infinity to okay, minus infinity 2 and 6, fair. Value finding minus infinity, index returned as 0. So we'll try to change that. Value finding is 3, index returned is 2. Oh, okay. So here's a problem now, right? So in this case index is 2. It'll try to change this value, which will not work. What if we use regular bisect? Index return is 1 in this case. Index return is 2 still. This sucks. Oh no, if we use bisect and we always use index minus 1, it will work, right? So in this case index return is 1, 1 minus 1, 0 is the one we choose. Here index return is 3, index return is 2. So we're gonna always work with 1. So we're gonna now just do a simple index minus equals to 1. Now things should seem fine in every case. Output is 3, 5. Okay. Why is it 3, 5? Because now after candidate 1 is processed, this is 3, 5. Now the third employee is 4 to 10. So minus infinity to 4. Ah damn, our logic is incorrect. Because when minus infinity to 4 comes up, then it belongs into multiple different. So it needs to be there can't be binary search here then. It needs to just check for all different ones. So like for every free candidate, it will go through all the candidates and just see if there's some intersection. So let's try to do this. So this entire index drama won't work. What we need to do is we have a free candidate. We'll go through for k in range candidates. We don't even require this candidate start anymore. So we can get rid of that. Although I have a feeling that as soon as we get rid of this, our solution kind of turns into n square problem. Anyway, let's try this and let's at least submit something, even if it's time limit exceeded. So for k in range candidates, right, we pick up intersection. So intersection would be max of x some or cand is candidates k. So we're gonna do can 0 and pre-candidate 0 common of can 1 and free candidate 1. Now once we have something like this, intersection is possible, right? We need to just check that if intersection 0 is less than intersection 1. That is the only criteria. Is it like that? That intersection 0 can't be greater than or equal to. Right? That is the only thing. Then we can kind of change candidates k to intersection. Range of len of candidates row. So minus infinity to 1, 2 to 5, 6 to infinity, minus infinity to 1, 3 to 5, 6 to infinity, minus infinity to 1, 3 to 4, 10 to infinity. And now when it goes through this, infinity ones get discarded and 3 to 4 is the only thing left. I am like almost 100% sure this is going to give us a time limit exceeded. If it doesn't, I'll be like surprised because of the length of the inputs that they've spoken up. Let's just still do a complexity here. So we are given that schedule length for any one. Total there are about 50 employees, and total work times also would be 50, but starting and ending can be anything. So now what we are doing here is we are going through this. This is the which can run. So that, so let's just say this is n, right? So this is gonna be n into this is n square. This itself is n square. But inside what we are doing is of 1, of 1, of 1, of 1. This is okay. 2 only, so 2 doesn't count. Length of candidates. So whatever candidates we'll have. So this candidates could itself be n, right? So 50 are there, maximum 49 could come up. Yeah, max to max 49, or it will be lesser than 49. So here again we are doing 50 into 50 into 50. That's like 1000 only. It actually might get submitted. I'm not sure now. I'm feeling it might get submitted because we are only dealing with starting and ending points. Let's try this. I've not considered 45, 56, 89, 86, 521, 57. Output was supposed to be 56, 57, but we've gotten okay. So the problem here is that when we find an intersection, is it always good to change the previous guy, or is it better to append this intersection? So in this case, what would have happened is 45 to 56. So 56 to 89 would have been 1, right? And here we have 21 to 56, 21 to 57. How is this 21 to 45 coming up? It's coming up because there's a minus infinity to 45. And when you couple that with 21 to 56, we'll get a 21 to 45. Yeah, we will get a 21 to 45. And now only if that 21 to 45 has, you know, like we should change It should have changed minus infinity, right? So let's try this test case actually. For minus infinity to 5, which would have come up here, it would have checked and it converted this. Uh, then what's happening is here 21 to 57, and it would have checked, and it's checking all these candidates. Minus infinity to 5, 56 to 89. Hmm. So the problem is that we need to not change the existing candidates. For after every new employee, there will be a new set of candidates essentially. So we will have this whole thing, new candidates, and whenever we find an intersection, we're gonna append that new candidates, not append intersection. And every time at the end of this thing, new candidates. Oh, brilliant. So for it won't submit for some very simple case of empty schedule or something. I'm sure it'll give some wrong answer for that. Output limit exceeded. Oh, wait. We'll just remove this print and see if it gets submitted. It can go time limit exceeded. That's fine with us. Yes. We solved a hard problem. Yay! It's not at all fast. Memory usage is less compared to others, so it's fine. But good to have solved a hard problem.